Okay, let's look at the IP packets this time. So we looked at an overview. We talked about the TCP packets and the UDP packets. Now let's look at the IP packets. IP occurs on the network layer. I'm sorry, I don't have a cool little acronym for you. If you know what an IP address is, it's easy enough to remember that it's on the network layer. Or if you really want to, if you're using the TCP IP model, then I for IP and I for internet, right? So either way, that's the layer we're on. So we're on layer 3 in the OSI model. Right? What's important on this slide? Here, this one. There we go. Enables TCP IP to inter-network. What does that mean? Well, TCP IP works great if you're on a single network. One device, right? Only one MAC address, port numbers are right on the surface. But once you leave your network, you need IP, right? So the IP address helps you get in and out, and it's routable, right? It is unreliable and connectionless. No, it doesn't mean it fails. Obviously, it's reliable. It's been around for, let's see, IP6 has been around for 22 years. IP4, much, much longer than that. So it's a fairly reliable system. What we're talking about is that there's no guarantee of delivery, right? IP addresses point you in the right direction. It doesn't wait around to see if it got there, right? It's connectionless, no three-way handshake like TCP is, right? It doesn't wait to confirm that you are who you say you are. This is part of the reason why Wireshark in promiscuous mode works so well. Your network card hears everything and just ignores the stuff that doesn't belong to it, right? So when you switch it to promiscuous mode, Wireshark is going, oh, here, pass it up. I'll listen to everything, right? IP depends on TCP to get that packet delivered to the right application. How does it determine that? Port number, right? So TCP handles that stuff. IP doesn't care. Two types of IP addresses, IP version 4, IP version 6. We haven't dealt and won't deal for a little bit of time yet with IPv6, but IPv4, 32-bit addresses, we're still dealing with those. Right? That's what we predominantly use on a network for various reasons. Give you some idea. 2, right? It's base 2, raised to the 32nd power. Well, why? Because it's a 32-bit address. Gives you 4.3 times 10 to the 9th addresses, and they are all gone. Well, at least all the public ones were, or are. All the public addresses have been doled out, used, reserved, held by whatever ISP holds them, or whatever, you know, big computing superpower holds them. Right? That's not including the private ones. The private ones, yeah, they're technically all gone too, but it doesn't matter because those are internal private addresses. You use your router to route between external public addresses, so we can reuse those as many times as we like, which is pretty much why IP version 4 is still around. It's just easier to deal with on an internal network. You can still route to a IPv6. That's not a big deal. It's just easier to deal with, smaller amount of numbers to remember. IPv6, it's 128 bits. So you raise 2 to the 128th power and you get 3.4 times 10 to the 38 addresses. That's a cool number to remember to impress people at parties. Well, I don't know what kind of parties you hang out at, but the parties I hang out at, that might be impressive, right? That's a poop ton of IP addresses. But because it's 128 bits long, it's not something you rattle off the top of your head. There are formats to them, make it a little bit easier to identify what they're doing or what that address belongs to, but they're just huge. Right? Here is the IPv4 stack, right? So here's the header, right? That whole thing. I don't know why I bothered drawing that bracket. There's a bracket there already. It just gives me something to do. Right, so notice it's all broken up just like the TCP header, bit 0, all the way over to bit 31. So 32 bits wide is how this is portrayed, right? And, you know, broken up into different areas. Flags only occupies a small, I believe that's a 4-bit section. So there's only a 4-bit flag, 4 zeros or 4 ones, unlike the TCP flags, which were 16 bits, right? What protocol, right? So TCP, UDP, etc. That's in your IP version 4 packet. Why do I point that out? Because it's not in IPv6, right? Header checksum, notice it's a header checksum. It checks to see if the IP header was corrupted, right? It doesn't care about the data, it cares about the IP header. Why doesn't it care about the data? Well, because TCP has a checksum and the data is below that, right? So you're already checking that on different levels. All this checksum is doing is checking to see if the header is right, which is why it only occupies 16 bits, right? Source IP address, destination IP address, 32 bits, right? Oops, 32 bits. Right. No duh, because we know, 192.168.1.1 is a 32-bit address because it's 4 octets, right? So we're very familiar with that, so it needs those 32-bit widths to do it. Options, we talked about padding and TCP, same thing here, and then your data. Again, I circled TCP because now, in terms of the IP packet, whatever the TCP header was, that's considered part of the data as far as the IP packet is concerned, right? Again, pause the video, look over these, make sure you understand what's going on. Internet header length, right? IHL, before it was just an abbreviation. Differentiated services, what are those? I'll let you read through those. I'm not going to sit here and read them to you. Gives you some idea of what's contained inside this header, right? And it continues. Look at this slide as well. What's inside it? I will point out time to live was originally meant, hours, minutes, seconds, right? But nope, no more. Now it's hops. How many times is that packet passed along by a router, right? That's its time to live. So it's not a minutes, hours, seconds time, even though initially it was. It's now how many times has this packet been forwarded along to another router? That's what the hops are, okay? So you give it a number of packets before it's eventually dropped, just not retransmitted, all right? Source IP address, destination IP address, duh. Hope you know what that is. So take your time, look over these slides, pause the video for a minute, and make sure you understand what's going on there. Again, a screenshot from Wireshark, and we'll look at something very similar to this in one of the activities, right? So, header length, total length, flags, 4 bits wide, 1, 2, 3, 4, right? So what the flags are, again, spelled out in the protocol. Time to live, 64 more hops. It can only go 64 more times before and if it can't find its destination, the packet is dropped, right? Source address, destination address, etc., etc., etc. Okay, so that's the actual packet. If we were looking at the data, it would be nothing but a series or a stream of zeros and ones just coming across the line or flashes of light, but we can interpret those. Why? Because it's a protocol. Come on now. And I know that when I'm at bit 33, I know exactly what that's supposed to be because the protocol spells out what those bits are. Here's IPv6. Here's the stack. Notice two things really important. First of all, port. Nope, doesn't have a port. Don't know. A lot of the information that was in IP version 4 is not here, right? There's a lot of stuff missing. Checksum. Nope. Nope, not there. Isn't there. The other thing you want to notice is there's 1, 2, 3, 4 levels of 32 bits. 32 times 4, boys and girls, 128 bits. Why? Because that's how long the addresses are. You need 128 bits for your source address and 128 bits for your destination address, right? IPv6 is IoT, Internet of Things. Pretty much everything acts like a public address, or can, right? That's what we're talking about here. So the most important thing is the unique identifier that says this is where it's coming from and this is where it's going. All the other stuff, guess what? TCP knows what port it is. So when it's de-encapsulated and IP gets removed at the transport layer, the port information is still in there. It's just not part of the IPv6 header. And again, here's what it all means, okay? A couple less screens for this one. So take a look at them, pause the video, see what that is, right? Hop limit, source address, destination address, fairly straightforward, but this one's a lot easier. There's not as much to worry about in IPv6. Pause the video, take a look at these, make sure you know what's in each of those. All right, and again, Wireshark. All right, screen capture looks a little different, but here's your Internet Protocol header, your IP header. Here's the information in it, right? Payload length, hop limits, source address, destination address. There's really not much to it, right? It's a much, much smaller header, which means it's slightly more efficient. Though bits wise, I'd have to check on that. If the bits header is still a multiple of 32, but is it as big as the IP version 4? I'm not sure on that. Right? And that's pretty much it for the IP header. So remember, data, you encapsulate that inside TCP. You take the TCP and the data, you encapsulate that inside the IP, right? So you're layering information on top of the data, and when you get to your destination, it's pulling that information off. Each device or each layer is reading what it knows and passing the data up the ladder until you finally get to your application and you open your web page or your Word document or whatever it is, right? So it's actually an ingenious system for delivery. If you have any questions, you know where I'm at.